Hello all, welcome to Engineering Economy course. We continue our discussion on cost concepts and design economics. In our previous lecture, we talked about maximizing the profit. We talked about the total revenue, total cost functions, and we considered the break-even points where the total revenue is equal to the total cost. And we said that there are two scenarios depending on the dependence of the price to demand. In scenario 1, in our previous lecture, we considered the case where the price was a function of the demand. And in today's lecture, we will consider the second scenario where the price and the demand are independent of each other, and we will see how this break-even point occurs under this scenario. We will also consider, in today's lecture, we will also consider cost-based design optimization. So let's get started. In the second scenario, we will assume that the price is independent of the demand. So in previous scenario, remember we said that we assumed that the price was depending on the demand. But in the second scenario, we will assume that this price is independent of the demand. So what does it mean? When the price is changed or the demand value will not be affected from these changes in the demand. And of course, if in this case, the price per unit is less than the variable cost, remember we have the fixed cost and the variable cost of the items. If the price is less than the variable cost, there is no way that you can do a profit, you can make a profit. Okay, therefore this price is assumed to be greater than the variable cost, unit variable cost. So under these two assumptions, we can write the total revenue function as price times demand. This is already what we were doing or what we did. But here, with this assumption, we will write, in order to find the break-even points, we will have, okay, for break-even point, we will have total revenue, which is P times D. Remember, for break-even point, we are writing total revenue should be equal to the total cost, or sometimes, as I told you, we are writing this as CT. It's just a notation. So total revenue is equal to the total cost, and P times D is the total revenue. And what is the total cost? It is fixed cost plus the variable cost, and variable cost is equal to the variable unit variable cost multiplied by D. And now this P is independent of the demand. In scenario 1, we assume that it is also a function of demand, and we say that it is A minus BD, but here we assume there is no such relation. And then using this equation, we can simply leave the demand point on one side, and we will have P minus CV times D is equal to the fixed cost. And from here, the break-even point D appears to be at fixed cost divided by price minus unit variable cost. So this value over here is the break-even point. And remember, in scenario 1, we had two break-even points. And the shape, if you remember, the shape was something like this. We have the total cost, and we have the total revenue functions, maybe something like this. And this point and this point are where the total revenue was equal to total cost. And we had two demand points where the total revenue was equal to total demand. But here, as you can see, we have just a single demand point, a single break-even point. And if we sketch the graph of these two functions, total revenue function, it is P times D. So in this axis we have D, and when we sketch the graph with P times D, we observe this line over here. And for this line, the slope is equal to P. Okay, the slope of this line is equal to price. And on the other hand, this total cost function starts from this CF value over here, and its slope is CV, which is the unit variable cost. And we said that price is greater than CV, so the slope of total revenue function is greater than the slope of the total cost function. And these two functions intersect at a single point, which is this one over here. It is D prime, and the value of this D prime is, as we calculated, CF divided by P minus CV. Okay, so this is the total, this is the break-even point when price is independent of demand. So we assume that here P is greater than the variable cost. What happens if it is less? So let me sketch here quickly. If it is less, this total cost function will start from CF and increase at a slope of CV, and this is the total cost function. Total revenue function will start from 0 because its value is P times D, and since the slope of this, since P is less than CV, it will go in this way. So the slope here is P, this is the total revenue function. And as you can see, they don't intersect. There is no break-even point here. And as you can see, this difference over here at any point is the value that you are losing. Okay, you cannot make profit in this case. And as you can see, for the region when the demand value is less than the break-even point in this alternative, we are losing. Okay, so this region over here is the region of loss. And if the demand is larger than this value, we are making profit. And the maximum profit appears at the maximum demand level. As you continue to increase demand, as you continue to sell more and more products, you make more profit when the price is independent of the demand. So we already did these calculations. These are just the same calculations, all summarized here, and the break-even point is this much, calculated in this way, and we have just a single break-even point, and to have that single break-even point we need to have these two conditions to be satisfied. Okay, now let's solve an example to understand the concept better. So at this point, please stop the video and read the question and try to solve it by yourself, and after that please restart it and check your solution. Now please stop the video. Okay, I hope you worked on this example by yourself. Now let's consider it all together. So an engineering consulting firm measures its output in a standard service hour unit, which is a function of the personal grade levels in the personal staff. Okay, I didn't understand anything. So you may feel like this. You didn't understand anything, so you will not be able to solve this question. But as I told you in the previous lecture, this is the story. This is the story of the question. Continue to read and you will understand what's going on. The next sentence, it says that the variable cost, and it already provided us with CV, this is the unit variable cost, it is $62 per standard service hour. Look, we say that this is the unit cost, unit variable cost, and what is our unit here? It is the standard service hour. So per each service hour, the cost is $62. Then it means that this standard service hour unit is now this that we measure our cost in terms of this. Okay, let's continue. The charge out rate, and it says this is the selling price, charge out rate, is 85.56 per hour. Okay, good. Then we already know CV, we already know P. Next sentence, it says the maximum output of the firm is 160,000 hours per year. Okay, this is something that we don't know. In our formulas until now, we didn't have such a thing. We don't know what is this. So let's keep it. Let's keep it and continue to read and see what it will ask in the question. Maybe this is an unnecessary data. Maybe we will use it for some other reason. Okay, and it's fixed cost and CF. Look, in this example, all the notations are also provided. CV, P, CF, everything has been provided. But the thing is, in a quiz or in an example, these notations or these definitions may not be given in that way, but instead it may be said that the cost changes with the standard service hour, and it's $62 per standard service hour. And from this statement, you should understand that this is the variable cost and it is CV. Okay, so be careful. Try to understand these data, what these data are. Okay, and CF is given in this way, and it asks the questions. For this firm, what's the break-even point in standard service hours and in percentage of total capacity? Part A of the question is this. Let's calculate. Okay, in the first part, it asks what's the break-even point in standard service hours. Let's first calculate this one. So A, and I'm going to calculate the next part of the question after this. Okay, when you have such a question, it is better to take these notes. So we have CV $62. We have P equals $85.56. Again, the units of measures are also important per service hour. And CF is $2,024,000. Okay, and we also have this 160 hours per year, which we don't know what it is, but you can say that this is the capacity, and capacity is 160,000 hours. This is the data of the problem, and we categorize them. Now in part A, I don't want you to memorize anything. We want you to know the concept. It asks for the break-even point, and the break-even point is where the total revenue is equal to total cost. And the total revenue is equal to P times D, and the total cost is equal to the fixed cost plus the variable cost, and the variable cost is equal to unit variable cost multiplied by D. So simply we want you to solve this equation, that's all. So let's just plug in the values. P is 85.56 times D, okay, and we want this to be equal to 2,024,000 CF plus CV 62 times D. We want to solve this equation for D, and from here you will get the break-even point. If we denote the break-even point with this D prime, simply you will have 2,024,000 divided by 85.56 minus 62, and you will obtain 85,908 hours per year. Of course, it's important to know what this output is. This is the standard service hours. Look, it says what's the break-even point in terms of standard service hours, and it is 85,908 standard service hours per year. This is the first part of the question. In the second part of the question, it asks that in percentage of total capacity. Okay, we found this value, but this is the break-even point. But in the second part of the question, it asks for the break-even point as a percentage of total capacity. And what is the total capacity? It's given here. Okay, the total capacity is 160,000 hours. So if we use 85,908 hours, what is the percentage of this one? So simply we will divide, so for percentage, 85,908 divided by 160,000, you will calculate that this is 0.537, or we can simply say that 53.7% of total capacity. So the break-even point occurs when we use 53.7% of our total capacity. Okay, this is part A, solution part A. Part B of the question asks a very important concept. So let's first read it. What is the percentage reduction in break-even point? It says sensitivity. If fixed costs are reduced by 10%, there is a semicolon here. If variable cost per hour is reduced by 10%, and if the selling price per unit is increased by 10%. So please try to understand the question so that when you understand it, the solution is quite easy. So we use some data to solve this problem. What are these data? We use the variable cost, we use the price, we use the fixed cost. And it says that, okay, this is the fixed cost. We know its value. But maybe the fixed cost will be higher than this one or lower than this one. We are not sure about it. Then, for example, if the fixed cost is 10% less than this value, what will happen to this break-even point? Will it be larger or will it be lower? So currently, when we solved this problem, we obtained, let's say, this graph. This is the standard service hours, okay? And we have this total revenue, and we have this total cost, and the break-even point appeared at this point, 85,908 hours. Okay, if the standard service hours is less than this value, we are losing, otherwise we are making profit. This is what we found until now. And now it says that, okay, if we change this fixed cost from this value, if we increase it by 10%, what will happen to this break-even point? Will it be higher? Will it be lower? Of course, without solving it, you can answer it. If the cost reduces by 10%, fixed cost reduces by 10%. Remember, in this graph, fixed cost represents the starting point of the total cost function. This is the total cost function. And if we reduce it by 10%, this CF new, and then we will have such a total cost function, and the new break-even point should occur at this point. But how much less? It's important for us to identify how much less. So actually, in this part B, we will consider these one by one. We will first consider the fixed cost. What will happen if we reduce it by 10%? Then, independent of this one, we will consider the variable cost. What will happen if this is reduced by 10%? And again, independent of this, we will consider what will happen if the price is increased by 10%. So this part B of the question consists of 3 separate questions actually, but they have the same idea. We are analyzing the results with respect to the changes. And this is called sensitivity. We are trying to understand how sensitive is the result to these parameters. Okay, so let's solve it. Again, this is the solution of the first part of the problem. Just a summary, for part A, we make total revenue to be equal to total cost, and we calculate the break-even point to be this value. And when we find the ratio of this one to the total capacity, we calculate the percentage value of this break-even point. Now, part B. In this part B, first we will consider this 10% reduction in the fixed cost. Okay, so 10% reduction, what does it mean? Remember, our fixed cost was 2,024,000. Okay, and we will reduce it by 10%. So what does it mean 10%? 0.1 times 2 million, 0.21,000. Okay, so this is the 10%, and we reduce this 10% from itself. And simply, if you take this in parentheses of this one, it is 1 minus 0.1. So 10% reduction simply means that multiplying this value by 0.9, right? So in this calculation now, what we do, we multiply the fixed cost by 0.9, and this is P minus CV. And what happens? The new break-even point, remember this shape, the break-even point here was 85,908, and when we reduced the fixed cost by 10%, new break-even point appeared to be this one, and it is 77,318. And now we calculated the new break-even point, how much this break-even point changes. But of course, other than finding this, it's also important to calculate what was the reduction percentage in the break-even point. Initially, it was this much, and the new value is this much. So what is the reduction here from the original value to this new one? In order to calculate it, we first calculate the difference and make the ratio of this difference to the original value. And we see that the result is 0.1, which means a 10% reduction. So what happened? When we reduced our fixed cost by 10%, the break-even point reduced by 10%. 10% reduction in fixed cost resulted in 10% reduction in break-even point. This is part A. Let's consider the second part of the question. It asks for what happens if 10% if the variable cost is reduced by 10%. Again, we are keeping everything else the same. The fixed cost is the original value. We just need to change the variable cost by 10%. And this 10% reduction means, again, multiplying the initial value of the variable cost by 0.9. So as we do it here. And when we calculate this value, we find that the new break-even point is this much. Now let me show you this case on the graph, what happens. This is our graph. There's no change in the total revenue function. Total revenue function is this one. The fixed cost is the same. It doesn't, initially, the fixed cost and the variable cost is this much, and we have this break-even point. This is the original, 85,908 hours. Now, if we reduce the CV by 10%, we are reducing the slope of the line by 10%. So we are starting from the same CF, but with a different slope. Okay, so this is the modified one, and the new break-even point appears here, and its value is 68,011. And as you can see, in the previous version, a 10% reduction in CF resulted in this break-even point, but a 10% reduction in the variable cost resulted in this one. Similar to the previous case, if we calculate the percentage reduction in the result, we obtain that a 20.8% reduction occurred in the break-even point. So when we reduce the variable cost by 10%, the result, the break-even point, is reduced by 20.8%, almost doubled. But in the previous one, 10% reduction resulted in 10% change, but here 10% reduction resulted in 20% change. When we compare these two with each other, what can we say? The results are sensitive, more sensitive to the fixed cost or to the variable cost? Of course, the change in the when we reduce the variable cost is higher. It means that it's more sensitive to the variable cost. Okay. Therefore, as a result of this sensitivity analysis, we understand that the results are more sensitive to the variable cost instead of the fixed cost. And finally, in the third part of the question, we are asked to analyze the increase in the price. What happens if the price is increased by 10%? Again, before solving it, let's try to sketch the graph and see what will happen, what can happen in this case. So here, the cost function is the original, it is the same. So we have this CF, we have this is total cost, the slope of this one is equal to CV. So initially, we have this total revenue function, the slope is equal to P, and this is the original break-even point, which is 85,908. Now we are assuming that the price is increased by 10%, and increasing the price by 10% means that changing the slope, increasing the slope of the total revenue function. And as we increase the slope of the total revenue function, this is the new version, so this P prime is greater than P, and the new break-even point appears here. And as you can see, the new break-even point is less than the previous one. But of course, how much less? In order to calculate that one, simply what we will do, what happened to price? Initially, the price was 85.56, and we will increase it by 10%. And increasing it by 10% means that taking 10% of the price and adding it to the original value. And if we take it in the parentheses of 85.56, it will be 1 plus 0.1, so it will be 1.1 times the original price. So increasing something by 10% actually means multiplying it by 1.1. And as you can see here, the fixed cost is the same, variable cost is the same, but the price is multiplied by 1.1. And the resulting break-even point is 63.01. So this value here is 63,021. Okay. Now, when you compare this result with the previous ones, with this one and with this one, you will see that the maximum change appeared here. And similar to the previous ones, when we calculate this ratio or this percentage of change in the results, we see that this difference divided by the original value results in a 26.6 reduction in the break-even point. So the change is the same, 10% change, but this 10% change resulted in 26.6% change or reduction in the break-even point. So as a result, when we compare these two, we will say that the break-even point is highly sensitive to the selling price. So the selling price is more important than the variable cost, and let me say in this way, and it is more important than the fixed cost. Okay, it is more sensitive to price than the variable cost and the least sensitive to the fixed cost. At this point, we will talk about this cost-driven design optimization. So as engineers, we do designs, we make designs, and these designs should be economically efficient and feasible. It should be justifiable so that we can implement those designs in real life. In order to explain this cost-driven design optimization, first, I want to introduce this example for you. And let's try to understand what's going on first. Okay, assume that the fixed cost for a steam line per meter of pipe is given with this formula per year. Okay, what do we have? We need to understand the problem. Assume we have this pipe. Okay, and on this pipe, per meter of distance, the fixed cost of this pipe per meter is this much. There's this X over here. What is this X? Around this pipe, we will cover it with insulation material. Let me sketch it with a different color. We will have some insulation material around the pipe, something like this. So the pipe is inside this insulation material. And this X is the thickness of this insulation in meters. Okay, what will be the thickness of this insulation material? And depending on the thickness, the cost of pipe per meter is given with this formula. As the thickness increases, the cost also increases. Okay, on the other hand, it says that when you increase the insulation material, what do you expect? The heat loss from the pipe per meter will be less as you increase the thickness, right? So when you look at these two functions, simply you can see this. Let me sketch a graph for you. This is the thickness of the insulation material. Okay, and this is the cost. And what happens as you increase the thickness, if it is 0 from this cost, I am first sketching this one. If this X is 0, then we have 50. So it starts from $50 and increases in this rate. This is the fixed cost with respect to this thickness, okay, per meter. Then the second one over here, if X is 0, you see that the heat loss is approximately infinite. But then as you increase the thickness, then you will have such a reducing function. And this is the heat loss cost of heat loss due to this thickness. And what we try to do is we try to find the optimal thickness value which will minimize the total cost. And the total cost is simply the summation of these two costs. And when you sum up these two costs, you will obtain such a total cost function. This is total cost. In order to solve this example, you don't need to sketch this graph. I just want to show you what's going on in order you to understand it. And when you look at this total cost function, the minimum appears at this point, and simply this will be the optimum thickness. And the question is, what is this? We want to identify. And look, in this example, what we do, we are making a design and we are deciding on one parameter of our design, which is the thickness of insulation material. And depending on this design, the cost changes. And we want to find the minimum cost as a result of this design parameter. Okay, this is called cost-driven design optimization. We are optimizing our design as a result of the cost. We will solve this example, but first let's see. What are the concepts related to this cost-driven design optimization. So as engineers, we must maintain a life cycle viewpoint as we design these products, processes, and services. So our design should include from cradle to grave. Okay. Also, in our designs, we should consider the environmental issues. It's becoming more and more important. What are these? For example, designing for energy conservation, the designing of an automobile bumper that can easily recycled. So these are some environmental related design criteria. So we can say that engineering is an economically driven art. Okay, so it's an art, we are designing something, we are creating something, but while doing this, we should do it in an economic way. While doing these designs as engineers, we should consider the initial investment cost of that design. We should consider operation and maintenance expenses. We should consider all other annual expenses in later years. And we should consider environmental and social consequences over the design life. So we should consider all life cycle related costs. Okay, so this cost-driven design optimization, as we have seen in the example, these are simple design models, and these are intended to illustrate the importance of cost in the design process. These examples or problems show the procedure for determining an optimal design using the cost concepts. Okay, we are not just doing making a feasible design, but we are designing it in the most economical way with minimum cost. So we will consider a single design variable in these examples, which will be X, and it will be named as the primary cost driver. Remember the example, the X was the thickness of the insulation material, and the cost of this pipe that we will install or design was depending on this insulation material. Of course, maybe the material of the pipe itself is also important, but this insulation material, cost of the insulation material may be much higher than that one. Therefore, considering this as the primary cost driver is more meaningful, and designing our product depending on this criteria, this parameter, is more relevant. So what are the cost-driven design optimization problem tasks? We first determine the optimal value for certain alternative design variable, and then we select the best alternative. And the best alternative these alternatives will have their own design variable values. Among those, we will select the alternative which minimizes the cost or maximizes the profit. So there are several cost types that are used or handled in cost-driven design optimization problems. Some of these are fixed costs. Some of these are costs that vary directly with the design variable, and some of the costs vary indirectly with the design variable. So the first one here says that when you increase the value of the design variable, then the costs increases. But the second one says that as the value of the design variable is increased, then the cost is reduced. So we may have both of these cases. So simply we can write the cost function in such a general way. So depending on our design variable x, some of the costs will increase directly with the design variable. So if we increase the value of x, the cost will also be increased. And some will be decreased with the value of x. So when x is increased here, then b over x is decreased. And this is the fixed cost. So it doesn't depend on the design variable. Okay? So this is a general representation. Of course, we may have alternative types, alternative formulas. And here, a and b are just the constants, depending on the problem parameters. So a represents a parameter for directly varying costs. B represents a parameter for representing indirectly varying costs, and K represents the fixed cost. Here, X represents the design variable, and we want to optimize its value. We want to find the value of X that minimizes the cost. So in a problem, this direct varying costs or indirectly varying costs, maybe they have different categories or subcategories. Okay, so but when we add up all those directly varying costs, we add up all of them, we obtain this part AX. When we have different costs which indirectly vary, a number of them, and we add them up and we obtain this second part. Here, maybe we will have several subcategories of fixed costs, and when we add them up, we obtain this K. So we are not saying that directly varying cost is just a one. Directly varying cost is a category of costs. Okay, it's a category, and we sum up all the costs inside this category to obtain this A, B, and K. So what's our general approach for optimizing a design with respect to cost? First thing is to identify primary cost driving design variable. In our example, it was the thickness of the insulation material. So we identified that one. The second is to write the cost as a function of this design variable. Okay, we need to come up with a mathematical expression. The third thing is we should, of course, if we want to optimize and the function appears to be differentiable, we will take the first derivative, okay, of the cost model, and we will set it equal to 0 to find its extreme point. Of course, sometimes this design variable can be discrete. It means that it cannot take any value, 5.2, 2.7. It cannot take rational values. It can just take some certain values given to you. Okay, then you need to select best one of the alternatives for all possible values. So when you take the derivative and make it equal to 0, solve it to find the extreme point corresponding to this design variable. But of course, we need to identify if this value minimizes the function or maximizes the function. In order to understand it, we need to take the second derivative and see if it is, for example, less than 0, then we will say that the function is concave and we just found the maximum value. Otherwise, if the second derivative is greater than 0, it means that the function is convex and we found the minimum value. Okay, so this is the general approach for optimizing a design with respect to cost. Now let's return back to our example. So in this example, we are trying to find the optimum thickness of the insulation material in part A. And let's try to solve it. So first thing is to write the total cost. Okay, so I'm going to write this as CT, which is equal to the fixed cost. I will write CF plus it will be cost of heat loss. Okay, so this CF, it is given in this way. Actually, the fixed cost is this part, which is 50 over here. The second part depends on the design parameter, so it's a directly varying cost. So simply you can write 50 plus 450 times x. X is our design variable, plus cost of heat loss is 4.8 divided by square root of x. So x to the power 1 over 2 is square root of x. However you like, you can write it. Okay, then look, we identified our primary cost driver, which is x, the thickness of the insulation material. We have an expression for the cost. Now, this is a continuous function, and we need to take the derivative of this function and make it equal to 0. And as I previously showed you, we have this fixed cost, and due to this heat loss, we have this one, and the total cost is something like this. And when you take the derivative and make it equal to 0, you will obtain this one. Now we want to find it. So let's take the derivative of this CT with respect to x. So simply we will obtain 450, and for the second one we will have negative 4.8 times this 1 over 2 the power of x divided by x to the power 3 over 2. This is the derivative of the second part, nothing else. Okay, and from here, when you solve for it, you find that x to the power 3 over 2 is equal to 2.4 divided by 450, and from here x appears to be 0.00533 meters. Okay, this is meters of insulation material. So when you multiply it by 100, it's 0.5 centimeters. Okay, so this is, actually I wrote this part wrong. This value is x to the power 3 over 2. And from here, if you find x, you will find it 0.0305 meters. Okay, this is the value of x. And it is like 3.05 centimeters. This is part A. Now, in part B of the question, it asks, how do you know that your answer in part A minimizes the total cost? Of course, if you don't know this shape, we will not know if this value, if this extreme point is a minimum point or a maximum point. So for this reason, we need to take the second derivative. So we will take the second derivative of the cost function with respect to x. And when we take the second derivative, we will obtain 3.6 divided by x to the power 5 over 2. And this value, this x, remember, it is the thickness. And thickness is always greater than 0. You cannot have negative thickness. So it means that this value over here is always greater than 0. And if it is greater than 0, then the function is convex. And since it is convex, the extreme point that we found is minimum. Okay, this is how we answer part B. And in part C of the question, we are asked, what is the basic trade-off being made in this problem? And basic trade-off is shown in this figure. As you increase the thickness, the cost of the pipe increases, but the cost due to the heat loss decreases. So the trade-off is between the cost of heat loss and cost of the pipe. And we find the balanced point. We find a point that minimizes the total cost of this. The trade-off is between the fixed cost, cost of the pipe, and the heat loss cost. Okay, so this slide just summarizes our solution as we did. The total cost is written in this way. Since it's a continuous function, we take the derivative with respect to x to find this one, and we find the thickness as this value as a part A of the question. And in order to understand that this is the minimum point, we take the second derivative and we observe that it is greater than 0 since the thickness is always greater than 0. So it means that this point is the minimum point. Okay, so we will continue our discussion on cost concepts in the next lecture.